Okay, here we have a challenging problem. We have a rubidium atom stacked together very nicely in arrangement A, and we have to find how many rubidium atoms are found in in a square that's 1 centimeter on the side. So if we start out with a drawing, we're gonna see that 1 centimeter by a centimeter square. Obviously the centimeter is a much larger unit than the angstrom, so you're gonna find a lot of rubidium atoms are quite nicely stacked in our A here. And then we have to find how many there are. So our goal is number of rubidium atoms in 1 square centimeter. Let's first start out with finding out number of atoms in a row and columns. To do that, we first have to convert the 1 centimeter, our length, to angstrom, because we are given the diameter unit as 4.95 angstrom. So 1 centimeter, from 1 centimeter we're going to convert this to a meter. So 100 centimeter is 1 meter, and then you have 1 meter that's equivalent to 10 to the 10th angstrom. So that shows the length of that 1 centimeter. And then you notice that, okay, let's first draw this. Okay, it's not perfect drawing, but you can see that this is like 4.95, and we have a uniform interval of this nicely stacked, and that's gonna show us, that's gonna give us the number of atoms. So 4.95 angstrom, that represent 1 atom, specifically the rubidium. Okay. You notice that centimeter cancel out, meter cancel out, angstrom cancel out, leaving you out only with the number of rubidium atoms. And when you calculate this, you're gonna get 2.02 times 10 to the 7th. So I'm gonna keep one more secret, just I will round it up later. Okay, you have that many atoms in a row or a column, because remember we also have the 1 centimeter for the vertical height. So how do we find the number of the rubidium atoms? Well, just square this. Okay, remember it's a row times column. You're gonna get total number of rubidium atoms in a given surface area. So 2.02 times 10 to the 7th, and then you square that, and you get, let's see, you're supposed to get 4.1 times 10 to the 14th rubidium atoms. Okay, that's A. Now we have to answer B. How many rubidium atoms could be placed on a square surface that is 1 centimeter on the side using arrangement B? So this is our focus now, and we have to find how many can be stacked. As you can see, there are less space, so you can assume we're gonna have more rubidium atoms quite nicely stacked in a given surface area. So, but if you notice, you're gonna see what? The same interval just as you saw here, right? In the arrangement A. Okay, so horizontally it's not really changing much, although there's some gap here, and then there's a gap in each row, so you might lose 1 atom. But seeing these many atoms, losing one is not gonna really hurt our calculation, as well as the fact that we have uh, the fact that we have to have the right sig fig. So we're gonna ignore some trivia here. Okay, so we're gonna first start out with the number of atoms in a row. Well, it's gonna be same as A. So 2 point in one row, in each row, uh, you have same number, 2.02 times 10 to the 7. So this is B, by the way. That was A. Let me box our answer. 2.02 times 10 to the 7th rubidium atoms. Now the tricky part is the vertical height. So I'm gonna first show you that this is what I'm gonna use. So I'm gonna first focus on the 3 circle. So let me try it. Actually, I'll draw a little more. Never mind. Okay, first I'm gonna really restrict our study. Just imagine yourself that 1 centimeter is extending up to just here. So in other words, don't count this and don't count that. Just imagine this is like our square surface. Okay, 3 by 4. Okay, never mind, just extend more. So if you have this, let me erase because I don't want you to get confused. Just imagine this is like a very simple 1 centimeter. What you're gonna notice is that you have a uniform height vertically. Okay. So you have a height that represents each row, and it's more squashed compared to this. Okay, you notice that there are 3 that represent each row, and then we're just gonna add one more at the end. Okay, that one is the radius of each ending atom. So let's first find this interval. So I want to know that. Okay, I want to know this. So the way how we tackle that is just connect the centers of these 3 circles, and you're gonna notice that's the radius, 1r, 2r, and because they are all radius, it's an equilateral triangle. So we have diameter, diameter, and diameter here. And then you can bisect this and make it perpendicular to the base, and then find the height. Okay, notice that equilateral triangle has 60 degrees and 30 degrees in the right triangle. And if you know SAT math, you're gonna realize that it has a nice golden ratio. So if you have a d over 2 because we have the base, and then you have a diameter here, and then you're gonna notice that the medium length is gonna be radical 3d over 2. So that's our height for each row in arrangement B. So how do we tackle this? Well, you first write down, okay, I'm gonna first start with the 1 centimeter again, and then 100 centimeter, 1 meter, and then convert this to pretty much same as the above. Okay, we've done this here, and Now in that length, we want to know how many height there, how many rows we have. So diameter is 4.95 angstrom, and notice units cancel out, and even the angstrom will cancel out, leaving you number of atoms. Rubidium. I could have expanded the way how I did in earlier problem like this, but this is another way to tackle it. You find the length. In that length, each height is this, then you can find the number of rows. Okay? And this corresponds, the 2.02 times 10 to the 7th correspond to the columns. Okay, when you punch these numbers, you're supposed to get 10. You're supposed to get 2.33 times 10 to the 7th atoms. Now you have the column. You have column, and we have number of rows. That means we can find the total atoms. There is a slight discrepancy. You've seen the gap, and also we didn't recount the very ending radius. But when you have this many atoms, and when we have to concern the sig fig, then this is not much a problem. So I'm just going to simply multiply this row by columns. So row, okay, let me row by column. You get like 4.7 times 10 to the 14th atoms of rubidium. So what does this tell us is we can pack more atoms in this hexagonal closed pack shape. Okay, by what factor has the number of atoms on the surface increased in going to arrangement B from arrangement A? Well, from B to A, okay, all we have to do is divide. Okay. It's asking the simple ratio. So to answer our C part, all you have to do is divide 4.7 times 10 to the 14th atoms versus the I believe it was 4.1 times 10 to the 14th. Now I highly recommend you keep a few more decimal points, and I think I got 712 and then 0.08, and then if you punch these in and you see how the atoms cancel out, and you get 1.15, but the problem had mostly 2 sig figs, so I'm gonna keep 1.2. So you have you can, in arrangement B, you can put 20% more atoms. Okay? And if extended to 3 dimensions, that's our last question. Which arrangement would lead to a greater density for rubidium metal? Of course, this is only concerned with 2-dimensional. If you have 3-dimensional structure, then you're gonna have way more atoms that can be inserted into our arrangement B. Okay, so to answer that, it's not really D. Okay. So obviously the answer is B. Would lead greater density because you have more atoms. Okay, that's it. Alright, thanks for watching.